This is the continuation of the same session. I got interrupted by an alarm, so I'm now back and continuing on. Now, we were talking about the creation of this so-called coefficient vector, and the components here, these c's, they are taken from the equation here of the hyperplane. This is the hyperplane equation, and you take these coefficients of the hyperplane and plug them into a vector. You create a vector u from these coefficients, and so each component here is the c from your hyperplane equation, and forming the vector u. Now, why do we do this? What's the point of creating this so-called coefficient vector? Well, it turns out that this coefficient vector is your normal, like that. So the equation of this vector will be u. That's what we aim to prove. Now, if that's the case, if this coefficient vector is your norm, your normal, like that, then any directed line segment in the plane, any arrow in the plane or the hyperplane, it should be orthogonal to this normal. And if it is, then this vector here, this u here, this coefficient vector, must be the normal if the dot product of this with any arrow, any directed line segment in your plane is zero. That's the definition of orthogonality. The dot product of those two vectors is zero. So we will show that the dot product of this coefficient vector with any line segment lying in the hyperplane, we will show that the dot product of that coefficient vector and the line in directed line segment in the plane is zero, and hence this vector here must be orthogonal to this. So in 3 dimensions, you just say that this vector here and this vector is they're 90 degrees to each other, and therefore this vector here must be the normal to this surface. Okay, so we're trying to show, and this is the n dimensions, that this coefficient vector u is the normal to the hypersurface. That's sort of the essential idea of all this. So what we're going to try to do now is we will form a directed line segment in this hyperplane, and then we will dot product it with this coefficient matrix, and we should get zero. And if that's the case, then this coefficient matrix must be the normal to this hypersurface. Okay, that's where we're going. That's what we're trying to do. All right, so let's form a directed line segment, so an arrow vector lying in the surface of the hyperplane. So this arrow from P to Q. So as a directed line segment, we can represent it as PQ with an arrow above it, right? So here, PQ, and we have to show that this line PQ lying in the surface, when dot producted with this coefficient matrix, coefficient vector, gives you zero. The dot product is zero. So by definition, this coefficient matrix dotted with this line segment, directed line segment, is zero, and therefore it's orthogonal. These two, this vector and this vector, because when you dot product them, you get zero. Therefore, by definition, this vector and this vector are orthogonal. So let's try to do that. Right. So here we're saying, so this vector PQ, here it is here, and we dot it with this coefficient vector u, and we aim to show that that dot product is 0. So we need to, and this vector here is said to be normal if this is the case, right? Now here's normal used in the adjective sense, but you can also say u is the normal in the noun sense. Normal can be both an adjective and a noun. All right. So this coefficient vector here is normal to the hyperplane. All right. So the proof. So let's find a vector that's from P to Q. So now the point P is a vector with these what's the word? Components. So a1, a2, an. Similarly Q, that's b1, b2, bn. And these 2 points lie on your hyperplane. They lie in the hyperplane. So this P and Q, they lie on this surface, this flat surface in say 3D space by analogy. Okay, so P and Q, these points, arrows, vectors, line segments, lie in the plane. All right, in the hyperplane. So therefore, these n-tuples, they're solutions to this. So if you plug in these components, values here, into these x's here, this left-hand side will equal b. So in other words, since P and Q lie in the hyperplane, these n-tuples must be solutions to the x's, because any point that lies in the hyperplane satisfies, makes the hyperplane equation work. The left-hand side equals the right-hand side. So we could plug in these components here into the x's. So x1 would be a1, x2 be a2, xn be an, and similarly for the b's. You'll be a different point in the space, but still, when you plug in these b's for the x's here, you still get b. Right? So P and Q are both solutions to this hyperspace equation. Okay? All right. So so it's just if you plug in the p values, the p components into the equation, you'll get b. And if you plug in the components of point Q in the equation, so these bi here, you'll get b. This b here. Don't be confused between this b and these b's. They're separate, different things. Okay, now from the previous question, 1.30, the vector v, that was the vector from the origin to, it was a vector that's parallel to this line segment and the same length, so by definition it's the same vector. And PQ by definition is, I can put 3 bars here, is Q vector minus P vector, right? We did that earlier. Now, okay, what is Q minus P? Well, this is just the difference, the sum in a sense, of, it's the vector sum. So you just add the corresponding components. So this will be the first component of Q minus the first component of P, and you do that for each corresponding component. So B1 minus A1, B2 minus A2, Bn minus An. Okay, so that's your PQ vector. Okay, now dot this with U. Now what is U again? Well, it's here. It's the coefficient vector. And you form this vector by taking the coefficients in your hyperplane equation. So the C1 here would go here, and the C2 here would go here, and so on. All right. So now dot this line segment with U, and we're trying to show that this dot product is going to be 0. We're trying to show that this coefficient vector is orthogonal to this line segment. This vector here lies in this hyperplane, and this vector we're trying to show is actually normal to it. It's sticking out like this, right? We're trying to show that this vector U is the normal, or is normal to the hyperplane. All right, so V is the same thing as PQ, it's the same vector. So PQ or V, now you just dot product. Now these are real numbers, we're talking in real space, okay? So we don't have to worry about conjugates or anything like that. So the dot product, the usual dot product, you take the product of the components and sum them. So what is V? Well, it's PQ. Well, what's PQ? So it'll be B1 minus A1 times C1 plus B2 minus, the second component, B2 minus A2 times C2, and so on. All right, so you get that form. So now rewrite this here. So you'll get B1 C1 minus A1 C1. That's here. Similarly here, B2 C2 minus A2 C2. You got it here, and so on. And Bn Cn minus An Cn here. Now rearrange this. Bring all the B's together. So you got a B here, a B here, a Bi. The Bi's. So B1 here, a B2, and so on, a Bn. So bring all those together, group them this way, and then put all the minus terms in another grouping. So you get minus C1 A1 plus C2 A2, etc., etc. Now, what is this? What is this? It's now this, where do we have it? I'm trying to find it. Oh, here. Oh, here it's in sort of condensed form, and here it's in expanded form. But effectively, look at this. It's of the form sigma CIBI, right? Sigma CIBI. But that's equal to B. So this is B. That's just B. Okay? And what's this? This is the long form, and this is the short form. Same thing. So this is just, if you put that into short form, it'll be sigma CIAI here, sum. But that is B, right? Because we got that here because point P with its coefficients A, it lies on the plane. It lies on this surface, hyperplane. So it's B. So this is B also. So you got B minus B, which is naught. And there it is. You've proved that this vector V is orthogonal. So whereas vector V is just this, right? So this vector here that lies in the plane, here's your hyperplane, so it's a vector lying in the plane, and vector U, if you dot product that with U, you get 0. So this U, whatever it is orthogonal to any line in the plane. So it has to be like that. So it's the normal, right? So we've shown that this coefficient vector is the normal to the plane. Interesting result. Okay, so PQ is orthogonal to U, and that implies the PQ dot, the dot product of a vector in the plane with the normal is 0, and that's end of proof sign. All right. Now last, this is the last question for this session. and then next session we'll start a new chapter, chapter 2, on the topic of linear equations. I'm jumping ahead a little bit. Okay, so question 132. Now, let's have a hyperplane, and we'll put it in 4 dimensions with real equations. So R4. So any vector that reaches a point in the plane will have 4 components. So we're talking 4 space, right? R4. Now let's call that hyperplane just H. Just H for hyperplane, right? And it will have its equation of the form C1x1 plus C2x2 plus C3x3 plus C4x4 equals some constant, say, I don't know, B, right? So that hyperplane, call it H. Right. Now, so let's see, how many parts are there here? 1. So is that all just 1 part or 2? Okay, just I'm not sure. Well, anyway, at least this is part 1. Maybe there's more. I'm not sure. Anyway, so what we're asked to do is to find the equation of that hyperplane that we called H for hyperplane, and you're given a bit more information that this particular point in 4 space lies in the plane. In other words, this point, this n-tuple, this 4-tuple, is a solution to your hyperplane equation, and we'll use that fact. And another bit of information you're given is that the coefficient matrix, in other words the normal U of the hyperplane equation H, is this. You're given, here's your vector U, and okay, so now what we did here, we took these coefficients and put them into this vector, and that was the normal vector. So these components here are the coefficients of the hyperplane. So these C's here are these C's. So before we went from this to this, but now here we're going the other way, right? We're given a normal equation. Now, with all that dot producting and the orthogonality that we did here, proved here, we know that this coefficient vector is the normal, right? It's this black pencil. It's the normal. So now we're given the vector for the normal. We're given U. So if we know U, we know these components of U. In other words, we know these C's, and these C's were taken from the hyperplane. So if we know these components, these numbers here, these numbers must have been these coefficients in the hyperplane equation. So our hyperplane is going to be of the form 2x1 plus 5x2 minus 6x3 minus 2x4. Because these 4 numbers here, they are the coefficients here. Because they're the coefficients in the normal. U is the normal. Okay, and we're given the normal. We're told here U is this. So these 4 components of the normal, U, they must be the coefficients of the hyperplane equation. So these are these C's here. All right. Now those 2 bits of information. So we're given the normal, and we're given a point in the plane. So that sort of makes sense. I mean, almost common. Imagine in 3-dimensional space. So you're given the normal, So here's your vector that's a normal, and it's oriented that way. And you know the plane, the hyperplane, has to be orthogonal to it. So if here's your normal, well then your plane has to be like that. Okay? But where is it? I mean, it could, I mean, the plane could be any one of these with along the same normal. But by specifying a point, like say at the point here, where my right finger is here, that's the point that this plane has to, this point has to lie in the plane. Well, so that means I have to shift up the planes so that the point lies in the plane. So that fixes the plane, because I got the orientation, if you like, of the plane, and I got a point that lies in the plane. That's enough to fix the plane intuitively. So let's actually find the equation of the plane. Okay, now the hyperplane equation, given these coefficients, has to be of the form 2x1, well, instead of talking x1, x2, let's just use x, y, z, and w, right? So x is x1, y is x2, z is x3, w is x4. Right? We just do it. They're just a relabeling. So these coefficients are from the normal. So you'll have 2x plus 5y minus 6z minus 2w is some constant. Right? That is the equation of your hypersurface. But we don't know what the constant is yet. So we haven't fully found the equation for the hyperplane. But we do know the point, this vector, this point, is a solution to this equation. Why? Because that point lies in the plane. It lies in the hyperplane. So we can plug in 3 for x here, and we can plug in minus 2 for y here, and 1 for z here, and minus 4 for w here. And this, because this point lies in the plane, this left-hand side should be equal to k. Right? It should satisfy the equation for the hyperplane. But these x, y, z, and w, they're concrete numbers, right? So we will get a number, and therefore k has to be equal to that number. That's a critical point, all right? So we can solve for k. So let's do that. So plug in this point into here, 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 and here. Calculate what the answer is, and whatever it is, k has to equal it. And so we know the value of k. And hence, if we know k, we have the hyperplane equation. Okay? Follow the logic? All right, so, well, let's do it. So 2x, so it'll be 2 times 2 plus 5 times y, so 5 times 5. Huh? Oh, here, sorry. 2 times 3 plus 5 times minus 2, minus 6 times 1, minus 2 times minus w, minus 4. So 6 minus 10 minus 6 plus 8. 6 minus 10 minus 6 plus 8. So the 6's cancel, minus 10 plus 8, that's minus 2. So k equals minus 2. So the hyperplane H, its equation is this equals 2. And here it is, 2x plus 5y minus 6z minus 2w equals minus 2. And that's the equation of the hyperplane, so we've solved it. And I'll stop here. Ciao.